Okay, so the next part of the problem is we're going to try to do the same thing in 3 dimensions. And so I built a little Zohm cube whose side length is 2. I divided it into how many small cubes when they're side length 1?
8.
8 of those. And I put circles on the inside, or spheres on the inside, that are supposed to be tangent to all the sides. But that hasn't actually happened. Right, because I don't have the right size. But you can see. And then what we're going to do is we're going to draw the sphere in the middle of this big cube that's tangent to all 8 of the spheres. So do you understand the problem?
Mm-hmm.
Yeah.
All right, so I'm going to take away the tennis balls and stuff. What are we going to do here? What's going to be the situation?
I wonder if we could use the same argument for the previous one, except using the space diagonal.
Okay. So what was that argument? We're going to draw a diagonal. This time it's going to be a diagonal in the big cube.
And then...
And how long is that diagonal going to be?
Well, that diagonal is going to be... It's going to be 2 of the diameters long plus 4 of the radii long.
Okay. So we're going to have the same equation, 2 diameters of the big circles,
Yeah.
of the big spheres, which is what?
1.
1, because they fit exactly in a cube. Do you see why this has diameter 1?
Because this side
I bring the small cube over. I don't even know why we have that small cube there, but we do. This has side length 1. We put it in, and it fits in perfectly.
Yeah.
So what's the diameter of the cube?
It would,
Diameter of the circle.
Sphere, sorry.
it would be 1.
1. Okay? So twice the diameter, which actually is just 2, plus the same argument from before. If you draw the long diagonal on our big cube, we're going to have a radius there, radius there, radius there, and a radius there. So those are our 1s.
Not to scale, but...
Not to scale. 4 times the radius of the cube, of the sphere, sorry. And what's that going to equal?
Well, we need to figure out what the space diagonal is.
Yeah, we got to figure out what the space diagonal of the cube
You
is.
can use the Pythagorean theorem because the diagonal on one of the sides of this... Actually, yeah, just pretend this is the big thing.
Yeah.
The diagonal on, like, let's say this side
Uh-huh.
is 2 root 2 because of the Pythagorean theorem.
Okay.
And then, so the space diagonal would be 8 plus 4. It would be the Pythagorean theorem, 2 root 2 squared plus 2 squared.
Uh-huh.
And the square root of that whole thing would be our space diagonal.
Okay, let's do it with the side length of the cube just being 1, and we're going to calculate the diagonal going from here to here.
Alright, and then we can double it.
Yeah, we can double it.
So, then this would be root 2.
Yeah.
And
Do you
this
see
is-
that? That's root 2. And it goes up 1.
So then we'd say it was 2 plus 1, and then that's 3, square root of that. So the space diagonal is root 3.
Okay, and so for our big cube,
It would be 2 root 3.
2 root 3. Okay. And so what's the radius this time? Can you do the calculation this time?
So you divide by 2 this time.
Okay, I divide
That's
by
right.
2.
So that would be 1 plus 4r
2r, because I
2r.
divide by 2, equals
root 3.
root 3. And now, can you solve for r?
So r is root 3 over 2 minus 1.
Close. Let's solve for 2r first. What does 2r equal?
2r is root 3 minus 1.
So what does r equal?
R is root 3 minus 1 all over 2.
Right, r is root 3 minus 1, the whole thing over 2. Remember what we got last time?
We got root 2 minus 1 over 2.
Okay, so we got root 2 minus 1 over 2. So we just solved the 3-dimensional case.
That's interesting. So in 2 dimensions we have a root 2.
Uh-huh.
In 3 dimensions we have a root 3.
Maybe in the 4th dimension we're going to have a root 4.
And what about in the 100th dimension?
Root 100.
Which is 10.
Yeah, and the reason that's coming is the Pythagorean theorem is just saying how far over, across, and up are you going?
Yeah,
And
so
we'll square that
you
each
only
time.
need those.
And so in 4 dimensions, we're going to go across, so over, across, up, and then 4th dimensional up. So we get 4 1s in our small cube.
And then 5 1s, 6 1s, all the way up to as many ones as you want.
So interestingly, this same process that we've gone through solves the problem in all dimensions for the radius of that circle, or sphere, or
It's
n-dimensional
2
sphere.
plus 4r equals 2 root whatever dimension you're using.
Yeah, or r equals, we could say r equals root n minus 1 over 2.
where n is the dimension that you're using.
Where n is the dimension that you're using.
Cool.
So that's interesting. So now here's the question. And let's go back to our two-dimensional picture. Okay, so here are the questions. There's 3 questions. So draw that circle on the inside.
Yep.
Okay, so question 1. Is there ever a dimension, and we don't have to, we'll answer these in the next video. Is there ever a dimension where the radius of the sphere, the n-dimensional sphere on the inside, is bigger than the radius of these? What's the radius of these?
It's always a half.
It's always a half. So is there ever a dimension where the radius of the small circle sphere n-dimensional thing on the inside is actually bigger than the radius of these? That's question 1. Question 2 is, does this small circle on the inside ever become so large that it actually goes outside of the cube? So it actually extends and like maybe goes out here a little bit. And then the final question, is there ever a dimension where the volume of this n-dimensional thing on the inside is bigger than the volume of the cube, of the n-dimensional cube?
Wow.
Yeah, wow is right. What do you think the answer to these questions
I
is?
think yes.
No. Well, no.
You think no, you think yes. Why
I
do you think?
yes for a few of them.
Okay, why?
Well, because like you can go to dimension like 10 trillion.
Okay. And why do you think things are getting big
Well,
in that dimension?
because the square root of 10 trillion is
Because we
going
have
to
the square root
be
of n.
huge.
Okay. Why do you think no?
Because these are always going to be tangent.
Yeah, it seems like you don't have a lot of room, right? It's
Yeah.
especially like, how can this thing go outside of the square?
Like then
Like,
these
how that doesn't even make sense.
these always stay in the square.
Okay. Now, let's see what happens.
Okay.
Okay.